welcome everyone to this very special lecture, which is part of the ongoing program. We just had the ICTS Distinguished Lecture on Monday, and I welcomed all of you and told you a little bit about ICTS, so I won't repeat that. But as I mentioned at that time, we have the ICTS Distinguished Lecture, we have the ICTS Ramanujan Lectures. These are special lectures that we host with the eminent scientists, and the Ramanujan Lectures are especially geared towards the mathematical sciences, and there's been a distinguished list of past speakers, and I'm very happy to welcome Professor Camillo De Lellis as part of this series, and we will hear his first talk, which will be at a hopefully a little broader level, and then further technical talks afterwards. So without any further ado, I will invite Professor Debayan Maiti to give a scientific introduction to the speaker.
Thank you very much, Rajesh, for organizing these lectures at the ICTS, and thank you to Camillo for accepting the invitation. Professor Camillo De Lellis is a faculty member at the Institute of Advanced Studies in Princeton, where he holds the IBM von Neumann Professorship. He received his PhD in 2002 under the supervision of Luigi Ambrosio at the Scuola Normale Superiore di Pisa. After 2 years as a postdoc, he joined the faculty at the University of Zurich in 2004, and he was appointed full professor in 2005. In 2008, he moved to the IAS. He has made seminal contribution to the fields of geometric measure theory, calculus of variations, hyperbolic conservation laws, and fluid dynamics. In particular, together with La'szlo, who is also here in this program, he has introduced the use of convex integration methods and differential inclusions to analyze the non-uniqueness issues to the Euler equations. His work has earned him an impressive list of honors and awards, including Stampakia Medal in 2009, SIAG APD Prize in 2013, Fermat Prize in 2013, Cacciopoli Prize in 2014, Amerio Prize in 2015, Boscher Prize in 2020, Feltrinelli Prize in 2020, and Miriam Mirzakhani Prize in 2022. In addition, he was a plenary speaker at the 2012 European Congress of Mathematics, an invited speaker at the 2010 ICM, and a plenary speaker at the 2022 ICM. We are very excited to have Camillo here today. The talk is entitled The Onsager Theorem and Beyond. So please welcome Professor Camillo De Lellis.
Thank you very much. It's a great honor and a pleasure to be here. My second time in India, in fact, because I was at the ICM in Hyderabad in 2010. And maybe one thing that I noticed is that I gave as a title the Onsager Theorem and Beyond. I'm not sure if I'm actually able during all this series of 5 lectures to go beyond. On the other hand, I think we had actually quite a bit of interesting talks about the beyond, for instance, in the talks of Hyun-Joo Kwon, and also in the lectures of La'szlo. So maybe I don't owe you that part. And I'm afraid for the experts in the audience that this is going to be boring, and for the non-experts of the audience that this is going to be non-understandable, but okay, that's life. The first thing that I would like to ask you is, how far can I actually go over here? Should I mean, can I go all the way up to here, or should I really... like here? Yeah. No, okay. Let me just put a line over here. Okay, so let me start by discussing the Navier-Stokes equations for incompressible fluid dynamics. So they take the following form. U is the velocity of an incompressible fluid in 2 or 3 space dimension. And so it's supposed to give you the velocity of the particle which is sitting at point x at time t. So it's a vector field depending on x and t. So let me put an epsilon in front of the Laplacian term. So this is the usual Laplacian, and this is the advective derivative of the vector field. And then I know that the divergence of the vector field is equal to 0. And then I typically, in this talk, I will want to actually couple the system of partial differential equations with some initial data, U0. And I am ignoring all the problems that can actually come if you have a spatial boundary. So I'm either assuming that you are on the whole space and that the fluid is kind of staying at rest towards plus infinity, or I'm thinking that you are in the situation of periodic boundary conditions, and so you can actually think that the domain is the periodic torus. Okay, so here I'm ignoring the fact that, so there should be some constant multiplying, for instance, the equation over here and over here, which is the density of the fluid, which I'm actually assuming, because the fluid is incompressible, is constant in time. And it's also constant in pace. So I sort of normalized it to be equal to 1. Okay, and this term over here is what I will call the viscosity. Although, to be the physical viscosity, I would have actually to put all of the dimensions inside. And so this epsilon for me at the moment is strictly positive, it's bigger than 0. And while you can actually think about this part of the equation as simply being Newton's law on the fluid, with some constraint which is coming from the fact that the fluid is divergence-free, the part which is actually over here is due to some dissipation effect, which is due to the fact that there is some resistance of the fluid to actually kind of slide, of layer of fluids which are actually sliding on top of each other. Of course, it's a very idealized situation that this friction is modeled in this way, and there's absolutely no thermodynamics in here. Okay, so there's no account for thermodynamics. Okay, nonetheless, these are the famous Navier-Stokes equations, and they're widely used to model fluids, even at the engineering level. So in a moment, I'm just assuming that everything is smooth. And so what do I understand by this? Well, if I take Einstein's summation convention, I'm just differentiating the vector field u along the direction di and multiplying by ui. Okay, so this is what it means. Of course, here I have the u. And now if I have a smooth solution, I can scalar multiply this equation by u and carry on some simple computations using Leibniz rule. And I discover the following conservation law. So the time derivative of modulus of u squared plus the divergence of modulus of u squared divided by 2 plus p, which is often called the head pressure in fluid dynamics, multiplied by u, this is equal to the Laplacian of modulus of u squared divided by 2 minus the modulus of the full derivative of u squared. And of course, there's the epsilon in front on these two terms. Okay, this is a very simple manipulation. Of course, when you multiply by u, you get dt of modulus of u squared. When you multiply u times gradient p, because u is divergence-free, you can write it as the divergence of p times u. And when you multiply by u over here, you recognize again the same way I actually got dt of modulus of u squared. Here you will get gradient of modulus of u squared divided by 2. And the reason why I can again put the divergence on this side is because u is divergence. A very similar manipulation gives you this. And if you have any kind of familiarity with the heat equation, this is a very well-known computation. Okay, so now if I integrate this equation in space, I derive then the following identity. Now, when I integrate in space over here, I will get the time derivative of the total integral of modulus of u squared divided by 2. If I have either a periodic boundary condition, or if I am in a situation in which the fluid is sort of at rest at infinity, I can actually integrate by parts this divergence, and I can integrate by parts this term as well. and assuming I have enough decay, actually put it equal to 0. Okay, and all of that I've done somehow so far is discovering something which I should have known very well from physics, which is that here I have just a law for the time derivative of the kinetic energy density of the fluid. If I'm assuming that the density, the mass density is equal to 1. And what I have over here is just a law for the decay of the total kinetic energy of the fluid, which decays because I have a dissipation term. Now, if I were in the ideal situation of epsilon equal to 0, in which this friction term does not exist, and that would be the Euler, the incompressible Euler equations, then this term would be equal to 0, and the total kinetic energy would be conserved, which is what you are expecting, because there is no external force and no external force and no internal mechanism for dissipation, and then this is kind of a system in which you expect the total energy to be conserved. Okay, so let me make this remark over here. So I have actually the Euler equation when I put epsilon equal to 0, and for the Euler equations, I would have conservation of energy. Okay, so now, at least formally, if you set epsilon to 0, right, you expect the Navier-Stokes equations to converge to the Euler equation, at least in some sense. And if you have a sequence of nice smooth solution with epsilon going to 0, which is converging to a nice smooth solution of the Euler equation, of course you expect, therefore, that this term is also going to 0, and that as you drop epsilon, the dissipation term is smaller and smaller, and somehow in the limit you get actually closer and closer to have energy conservation. Okay, formally you expect that, and if the convergence is smooth, let's say smooth enough, and in fact, in principle, you don't even need that much smoothness, because, you know, if when you're going down to 0, this quantity behave like epsilon to the minus 1/2, say, like 1 over square root of epsilon, which still would mean that actually your derivative is getting pretty rough because the total L2 norm is blowing up. This would still not offset this epsilon that you have in front. So I don't even actually need the convergence to be smooth enough, as long as it is not too irregular, I would say. Then you're actually expecting the term epsilon the term epsilon times integral gradient of u squared to vanish. Okay. On the other hand, it's one of the tenets of the famous theory of Kolmogorov of fully developed turbulence, that if you are in a turbulent situation, this is typically not happening at all. Instead, what is happening is that the limit of this quantity as epsilon goes to 0 stays bounded away from 0. So let's say statistically, in whichever sense you actually want to understand this, because from the mathematical point of view, there is not, I think, a rigorous formulation of this. But statistically, what you are expecting, or what you see, so you expect that, in fact, this quantity over here sort of stays bounded below by something, and you know, we will maybe sort of try to understand what is this something which is there. Okay, so this is what physics books actually tell you, but me as mathematician, I would like to see a proof of this fact from bracing principles. And so let's say, ideally, what I would like to see is a sequence of solutions to this equation, which satisfies certain natural kind of assumptions, with the property that when I let epsilon go to 0, the corresponding solution is actually seeing this phenomenon that epsilon times the integral of gradient of u squared epsilon. Maybe I should kind of index my solution by the parameter epsilon, because of course for different epsilons I actually see different solutions. And so this sort of remains bounded away from 0. So here somehow is the mathematical question. So produce at least non-trivial examples. So produce some non-trivial examples. Okay, what do I mean by non-trivial examples? So by non-trivial examples, I mean, first of all, that, I want, well, the way I actually formulated this over here, I want U0 to be a fixed initial data, which is independent of epsilon. And maybe this is actually a bad notation because it seems like, U0 would be the limit over here. So maybe let me call it U bar. Well, I mean, if I force you always to kind of use exactly the same initial data, maybe that's a sort of hard problem. But let's say that I allow you actually to even vary this initial data over here. So what would I actually require on the variation of this initial data to be, to still say that your example is somewhat meaningful? Well, certainly I don't want to inject more and more energy at the beginning, right? So if I'm putting actually an infinite amount of energy at the beginning, then somewhat I'm cheating, right? So you look at sort of, the total integral of this has to be the initial energy minus the final energy. So you see that if I'm actually injecting an infinite amount of energy at the beginning, probably I am kind of cheating. So first of all, I would say if you're varying the initial data over here, I want you to actually have a uniform bound on the L2 norm of the initial data. So I certainly want that at least. But I actually want also more. So another thing that I can do is I can actually put very oscillatory initial data. Like, I don't know, I could put sine of x divided by epsilon, okay, on some components, which is sort of making more and more wild oscillations and converging in a weak sense to 0 just by averaging. Okay, then I wouldn't be surprised that that example is actually giving you that thing over there, because even if I just take the heat equation alone, right, I would still dissipate essentially all of the energy pretty quickly, okay? Because the heat equation, somehow the viscosity would smear my solution right away. So let's say the minimum that I would actually require for this example to be sort of meaningful is that, there is a final U bar to which you're actually converging in the L2 sense. Okay, then it starts being like a very interesting example. A variation of this might also be the following. What happens if I actually put an external force over here, which is also depending on epsilon? Okay, if I put an external force, well, I might, for instance, even just hope that when the fluid is kind of very mixed, very homogenized, I'm even converging to some sort of steady state in which, in spite of the fact that I'm injecting always energy, I keep injecting energy that somehow the equation actually kind of dissipates, okay? So if you have a steady state with an external force, which is producing work, you would see immediately that you cannot have actually a solution of the final equation. So you might think of putting a force, but if you're actually putting a forcing term, then for the example to be kind of meaningful, the forcing term does not have to inject too much energy either. And in fact, the ideal situation would be that the forcing term is smooth, so that you're maybe like exciting only a few Fourier modes, okay? Or maybe even converging to a steady state. So possibly adding an external force but a smooth one. For instance, exciting only a few Fourier modes. Okay, so that is some sort of holy grail, which we are pretty far from getting, I believe, at least at the moment. But there are some exciting progress in that direction. Now, if you actually go further in the Kolmogorov theory of turbulence, one thing that actually it is derived is the so-called Kolmogorov 5/3 law. Okay, what is this? So this is simply the following consideration. Assume that you are in a situation in which somehow the fluid is kind of dissipating the energy in a sort of very homogeneous way, so that you see some sort of steady state in the distribution of the energy according to your Fourier modes. Okay, so if you're having something like this, so what is the law that you can guess on the total amount of energy, Ek, which leaves roughly at wave numbers which are between two wave numbers that you fix, say K2 and K1. So what is actually going to be sort of Ek over here? Okay, and so how does it relate in particular to the two quantities that you have over here, which is, so how does it relate to the dissipation rate, D, which is for me this quantity over here. Okay, and how does it relate to K? Okay, so if you make a very simple dimensional analysis, if you're guessing that there is a power law relation between these three quantities, this is what somehow pretty much many books would tell you. Well, you're going to look at what is the dimension of E of K, and so you're going to look at what is the dimension of the dissipation rate. So D is measured in unit of length to the power 3 divided by times to the power 2, as you can see somehow from the formula. And K is measured in inverses of the wavelength, so in inverses of the unit of length. Yes. Yes, yes, exactly, sorry. Yes, of course, the energy is the energy is velocity, so length squared over time squared, and I am dividing by time, right? Because I'm taking the time derivative. Yes, actually, what did I define as D? Yes, I defined as D this one, but of course, I could as well define as D this quantity over here, right? Because I'm assuming that I have the identity. Yes, thank you very much. Okay, so if you actually take this dimensional analysis and you see, I'm kind of thinking of, probably you don't want me to write over here, right? Let me make just one small exception this time. So now you postulate that E of K is equal to some, say, constant times the power, so D to the power alpha and K to the power beta. And now, if you're assuming that this constant is going to be independent of the system of measurements that you're using, you will actually realize immediately, it's a very simple computation, that alpha has to be 2/3 and k has to be 5/3. Okay, and you are therefore deriving what is called minus 5/3, right? I miss a minus. Sorry. Beta, yes. And so you're deriving what is called the Kolmogorov spectrum, which is telling you that the energy so the energy spectrum E of k should behave like d to the power 2/3 and k to the power minus 5/3. Okay? Okay, that's very interesting. So you could go sort of a little bit further. So if you assume that you are in a situation in which kind of your fluid is essentially homogeneous, so in space and overall kind of Fourier modes. So if you're going to look at what is the amount of energy in a dyadic shell, okay, so the amount of energy in a dyadic shell, say, which is in Fourier space, so the wavelength to be between, say, 2, so the 2 to the n between 2 to the n plus 1, right? You will realize that the total, so the total energy, so which is going to be something like this. Right, so this guy is going to be roughly right, so it's going to be roughly modulus of psi to the power minus 5/3, so which is 2 to the minus 5/3 times n, times, of course, kind of the width of the shell, which is 2 to the minus n. And so it's going to be roughly 2 to the minus 2/3 n. Okay, and now if you kind of believe that you are in a sort of isotropic situation and so that all the Fourier modes at that level, they're kind of equally distributed, there is no big difference between the L1 norm of this guy and the L2 norm. So you're actually expecting that the L1 norm of u hat psi, so in an homogeneous situation, so you're expecting somehow that the L1 norm of this guy is also roughly, so when I have 2 to the n, that's so equal to psi, that's so equal to the n plus 1, is roughly 2 to the minus n divided by 3. And if you are familiar with the Hoelder spaces, this is sort of suggesting that you have a function which is at a Hoelder regularity 1/3. Okay, so this is related to having a Hoelder modulus of continuity of your function, which is of the following type. Okay, so now let me go a little bit further and let me just simply, yes? Yes, sorry. Yes. In the upper line? No, this is the wave number. I'm looking at the Fourier transform, yes. So K is essentially the modulus of my psi. Yeah. Exactly. Yes. No. No. It's like a Lagrange multiplier. So it's a part of the unknown of the system. Okay, so it's the hydrodynamic pressure. It's given by the resistance of the fluid to kind of occupy more space through the motion, right? So if all the particles would actually go, say, you have all the particles which are moving into a certain direction, which is kind of suggesting that the fluid should be compressed. That is actually not possible. And so the gradient of the pressure has to be understood as a reaction to that. So if you actually write down, say, if you're trying to derive the Euler equation as simply following Newton's law, so saying you're like trying to look at the critical point of a Lagrangian, and the Lagrangian would be the total kinetic energy, you are constrained by the divergence free motion to actually move with the flow of incompressible diffeomorphisms. And then if you like look at the Lagrangian under this constraint, this gradient of the pressure is coming out as a Lagrange multiplier for the critical point on that constraint, okay? So it's related, I mean, you solve the equation in the pair U and P. Yes, it's one of the unknowns. It also comes from a basic counting argument if you look at the number of equations. Right? I mean, you have a vector equation which has as many equations as the components of U, but then you have divergence of U equal to 0. So you have, say, in 3D, 4 unknown functions and 4 equations. Otherwise the problem would be overdetermined if you actually tell me what is the pressure P, right? Then you would have 4 equations for 3 unknowns. Okay, so now let me get to one of the names actually in the talk, which is La'szlo Sze'kelyhidi. So there is this famous paper in 1949 in which he is putting forward some ideas about a statistical description of fluid turbulence. And he's rediscovering some of the theory of Kolmogorov. But one of the things that he observes is that, okay, so the picture which is behind this is that there should be some sort of, so this is what is called an inertial range. So a range of Fourier modes in which this distribution of energy is actually active, right? This e to the k. And then at a certain point, there's the viscosity which is kicking in, and sort of the viscosity is actually quickly dissipating all of the energy which has been transported from, say, some low wave number to some high wave number, okay? On the other hand, if this mechanism is more and more independent of the viscosity, so when you actually let epsilon equal to 0, this inertial range actually extends all the way to infinity. Maybe one way to understand this is that you expect solutions of the Euler equations to have a similar behavior. So you might actually expect to find solutions of the Euler equations which have this Kolmogorov spectrum, and which as an aftermath would actually dissipate the total kinetic energy, even though there is no dissipation or no force acting in the equation itself, okay?
This goes as this and so forth, to a condition, to an inequality on the vanishing of U of x plus y minus U of x. I mean, the last expression you have, you give
yes. Oh, right. So, okay, what I have in mind is something like this. So your function will respect an inequality of this type if I say, put a little epsilon over here, and would not respect an inequality of this type if I actually put an epsilon above. So I expect somehow my function to be at the threshold regularity, which is given by this 1/3.
Yeah, so you're saying
basically it goes that way. Yes, sorry, I was a bit sloppy. And actually, like, because we are, you know, in comparing somehow sort of from the Fourier to the space side, it's not completely clear if I actually have to put maybe a logarithmic correction of something to in fact kind of like, you know, capture the exact asymptotic of the velocity when I'm going actually at small scales. Okay? But this is what you could actually reasonably expect for a say I don't know, random solution of the Navier-Stokes equation, which is realizing this kind of Kolmogorov spectrum, and this assumption that everything is homogeneous in space and in the Fourier modes. Okay, so it's a sort of reasonable thing to expect. Okay, so here is an Onsager observation. So if you are actually expecting that this picture is correct for every epsilon, at this point in an idealized situation, you could even just put epsilon equal to 0 and see what you can infer in that case. Yes, there are similar inequalities for higher structure functions as well. And in fact, if you really believe the Kolmogorov picture, there are similar inequalities for the higher structure functions. On the other hand, it is known that Kolmogorov's picture is not entirely precise. It needs some correction. And the some correction which is needed is due to this intermittency, which actually says that this homogeneity space of the turbulence is not a completely correct picture. And then there would be some corrections. Right, but if you actually look at, say, like at the third order structure function, okay, so that prediction is actually robust and correct. So for the third order structure functions. Okay, so coming to Onsager, so here is actually one, as a mathematician, like what I like is to get to some pretty concrete, as a mathematician working in PDEs, is what I like is to get to some pretty concrete PDE questions that I can try to answer, right? I mean, a yes or no. For instance, that which I post over there is a concrete PDE question, right? I mean, when you start getting into sort of, probabilistic or stochastic thing, I start getting nervous. So for instance, if you tell me that with probability 1 something should happen, then, the first thing that I would ask is like, okay, just show me one example in which this happens. Onsager actually put forward then the following conjecture, which, given the heuristic explanation or the heuristic discussion that I've given to you, it should sort of, look intuitive. So even when I put epsilon to 0, so even considering solutions of the Euler equations, something like this should happen. So if I have a Hoelder regularity on the solution, which is better than 1/3, then U satisfies the energy conservation, and on the other hand, I should find examples of solutions U which satisfy just a slightly milder condition, and violate the energy conservation. Okay, and in short, what is going to be the content of my next 4 lectures is to give you an account of how this actually can be made into a theorem. So this is in fact a theorem now. Yes.
So does it mean that when you say there exist solutions, is it enough to find a solution which satisfies this and then violates? Or is could there be a stronger statement that for every solution that satisfies this, it violates the energy? That's not true?
No. I mean, in particular, for instance, a solution, a smooth solution satisfies that. Okay. So, but I mean, even going there, so like there are solutions which satisfy that, which are no more regular than that, and that satisfy actually the energy equality. okay? So it's just a possibility that the energy is violated.
But one doesn't know how to characterize the space of such solutions which satisfy this and violate the energy. Is there like, amongst the space of solutions which obey this in a strict sense?
So first of all, let me also kind of remark one thing. So Euler is a completely reversible partial differential equation. Time is completely reversible. Like everything which is just based on Newton's law, and there's no thermodynamics inside. So when I say violates, of course, in Onsager's idea was that the energy should go kind of down. But if you give me an example in which the energy is going down, I can actually just simply reverse the time and get an example in which the energy is going up. So you're seeing an error of time only if you're coming from some approximation which actually takes into account like a dissipative mechanism like Navier-Stokes. Or otherwise, you have to bake in the definition of the solutions of the Euler equations that you only accept the ones which are energy dissipative and not the ones which are energy increasing. But then you sort of have to give that as an axiom if you want. Now, I don't know of the simple characterizations of the ones which are energy conservative compared to the ones which are energy dissipative or the ones which are energy increasing, or if you look at the mechanisms for producing these solutions, you can see that you can actually, that essentially, okay, when I will explain more about the mechanism which is actually producing these solutions, one thing that you might simply realize is that when you are at this degree of non-smoothness, really the energy identity that I gave you is violated in a such bad manner that I can essentially put it as a fourth or fifth equation to my system and try to actually solve for it, for any initial data. So in some sense, the non-uniqueness of the solutions given by, say, the first 4 equations is so brutal that this fifth equation is not anymore a constraint. It's like it doesn't exist anymore. So, and in that sense, the ones which are actually going to satisfy it, even just the PDE somehow, which I wrote, right, for dt of modulus of u squared divided by 2, is just a special subclass. I don't know, does that answer actually to your question somewhat? Okay. So now this is in fact a theorem.
Sorry to slow you down, but
yes.
I think as a physicist, I just wanted to know, would you expect the generic solution to be, in some sense, generic?
So there's some notion of genericity, which is not actually your usual notion, though. Like, it goes more into some topological notions, like, Baire category and so on, or like, density of these solutions, which, for instance, would tell you that you can approximate, you give me a divergence-free field with certain assumptions, and I can essentially approximate with a solution of Euler which is going to violate the kinetic energy in some way. So in that sense, you could actually say there is a kind of abundance of them. Okay, so back to my statement, this is in fact a mathematical theorem, but of course, before telling you what is a mathematical theorem, maybe the first question that you should raise is, what the hell do I mean that I am actually a solution of the equation if I am at such an assumption of irregularity that I cannot actually write down the equation itself, okay? So what does it mean for you to solve the Euler equation? Okay, so there are different answers that you can actually give. So the first answer was actually given by Onsager itself. So take the Fourier transform. Actually, he was looking at the space periodic case. So take the Fourier series and write down Euler as an infinite system of ODEs. okay? And when you write it down as an infinite system of ODEs, so you will have somehow an ODE for every coefficient of your Fourier series, and you will realize that to make sense of the right-hand side, so kind of the interaction of all the other Fourier series, L2 summability is more than enough. You just get a series that you want to sum, and if you are L2 summable is enough. And here you're even assuming that your function is continuous. Okay, so that's one possibility. Another possibility, so this is why what the modern mathematician would do, is to define weak solutions. And to define weak solutions, you just have to observe that you can rewrite the Euler equations in the following way, because your vector field is divergence free, so you can actually put one derivative out. And so you have to make sense of the product of U with itself, which means, for instance, if you are square summable, this one is going to be a summable function. You can make sense of this. And then you have to take derivatives of whatever you're left with, right? But I mean, if you have a distribution, you can take derivatives in the sense of distribution. And so the real problem is to be able to actually define this product. And once again, if you are L2, you are actually perfectly in business. But you can actually even take the point of view of continuum mechanics. That is that the divergence-free condition is nothing but conservation of mass. So the divergence-free condition, what really it means that the integral over any boundary of a fluid element of u dot nu is equal to 0. That is, there is as much fluid which is entering as there is actually fluid that is exiting. And you see that you only need continuity to actually make sense of this. And if you look at the momentum equation, which is like, the other system that I've written, there is an equally good formulation, which is just like, for each fluid element. And so for each fluid element, you want conservation of mass and conservation of momentum, essentially. So Newton's law and conservation of mass to hold. So here you have essentially an infinite system of equations for every fluid element, which means for every region omega, which is a sufficiently regular region of the fluid, okay? And what is actually the fun is that all of these 3 points of view, they are all equivalent. Whether I take a solution in the sense of Onsager, or I take a solution in the sense of weak solution, or I take a solution in the sense of continuum mechanics, they actually all give me exactly the same concept. Nothing more, nothing less. Okay, so what is then like, the upshot of my story for the next 4 lectures? Well, the upshot is that, first of all, this part of the conjecture, let me call it part A, has a very beautiful and simple proof, which is due to a constant in entity. Well, constant in A entity. I think in 1994, which was actually predated by a work by Eying, which got very close to it. So A holds. But it's essentially a kind of 2 pages computation, okay, which I will show you. It's really beautiful and elegant. And the other part, which is much more recent, and it's a theorem by Isett in 2017, is that B also holds. And the story will be how we actually got to this theorem. So there were, first of all, examples by Scheffer and Schnirelmann of very irregular solutions which do not conserve the energy. This was interpreted later, or it was kind of reproved later, but with bounded vector fields by La'szlo and myself in a paper which introduced this kind of idea that one could recover the Scheffer and Schnirelmann example by using convex integration. Okay, so this introduced some sort of new technology in the area to actually produce solutions like that. So I will explain you what is the convex integration for, say, bounded solutions, so without like a continuity requirement, and this is like our first paper, and then how we actually managed to produce continuous solution, which was in some sense maybe the most important barrier to actually break at that point. Okay, so first of all, for the story of the subject, so Scheffer and Schnirelmann, so Scheffer first in 1995, I believe, and then Schnirelmann in 1998, so produced L2 solutions in time and space. Let me write them in this way. So they're not solutions which have finite kinetic energy for every time. They're really solutions which have the integral of the whole kinetic energy bounded in time and space. Okay? So violating the energy inequality or identity. And actually, we will see they will be they violated in a very, very funny way because these are solutions which are compactly supported in space and time. So it means they start with some initial data which is identically equal to 0, and then they become sort of non-zero. Okay, so it's kind of very pathological solutions. Okay, so after that, there's a work by La'szlo and myself in 2007, in which we produced L infinity solutions, so bounded solutions. So there exists bounded solutions violating the kinetic, the energy identity. Okay, so of course you see that there's a big improvement because our solutions are bounded compared to just be in L2. In particular, they have bounded kinetic energy for every time, right? And this per se was actually a quite interesting improvement of that paper. There were even people asking whether this was really the reason of the pathology, because maybe you just assume that you are in the energy space and that pathology does not exist anymore. But beyond that, I think what actually was the most important point of this paper is that while the construction of Scheffer and Schnirelmann kind of looked very ad hoc, what we could show is that our construction was in some sense embedded into a tradition which existed before. So a construction in quote unquote a tradition which had a, say, 50 years history, depending if you want to go back to the work of the Nash isometric embedding, but in an attempt to be as fancy as possible, because as I actually heard, I think in a talk some time ago, as a mathematicians, you actually, a couple of days ago, you actually like to go back to kind of the oldest theorem that you can sort of, mention. So now this guy was actually able to go back till something like a couple of thousand of years before, because it was really going to the ancient Greek. So the best that La'szlo and I were able to do is just to say that, in a sense, the tradition goes back to Weierstrass's example of a continuous function which is nowhere differentiable. So far we could get to something like whatever, 1870, well, Riemann claimed this like 1850. It doesn't seem that we can actually go back to the ancient Greeks yet, at least. But okay, so that is maybe more kind of, stretching it, but certainly to something which had a 50 years history. And building upon this history, and in particular, drawing connections with the work of Nash on isometric embeddings, which I will explain in one of the lectures. So drawing connections to the isometric embedding problem. So again, La'szlo and myself, in 2012, were able to construct continuous solutions. Okay, and here we kind of felt that we really had broken a big boundary because we were stuck at that level for quite some time. And in fact, what happened is that almost immediately after our continuous work, because we had been understanding Nash work and the work of other people on the isometric embedding, we almost immediately actually produced a first example of some Hoelder regularity. Which violate the kinetic energy. Of course, again, always, all of these guys violating the kinetic energy identity. Okay, and of course, this spurred actually a lot of activity, and there's been contributions by Isett, Buckmaster, various combinations of, various subset of myself, so various combinations of the four orders. With improvements of this, of the first Hoelder exponent. But two groundbreaking papers then came, so one by Navier and Sze'kelyhidi, and then by Isett in 2017. So this was, I think, also essentially 2017, right, La'szlo? And what actually he did is taking the previous constructions plus these ideas, some of the ideas which were over there, plus another additional idea, they finally got to the Hoelder 1/3 solutions. And again, what I mean actually by Hoelder 1/3, maybe I should put a minus over here, is that for every exponent which is below, you will be able to construct a solution which actually violates the kinetic energy. Now, one final actually remark to this story. In a sense, this solution doesn't satisfy, it's a solution in which the kinetic energy is simply not constant, but it might be increasing or decreasing depending on where you're looking at. So there was a reworking of the proof by Buckmaster, myself, La'szlo, and Vikol, in which we also produce what are called dissipative solutions. Okay, so what about the beyond? Well, as you might have learned by listening for the people who were at some of the talks, somehow these techniques, which now go under the name of convex integration, which was not coined by us, was actually coined by Gromov for problems in geometry, and that we borrowed. And so these type of techniques have actually been used in a variety of different situations. In some sense, in certain situations, to just produce examples trying to understand which type of conjectures or which kind of expectations are actually legitimate when you're looking at low regularity solutions of a certain PDEs. So you can understand somehow the usefulness of these methods as testing whether some reasonable conjecture on a certain concept of solution is correct or not. For instance, a famous result by McMaster and Vicol on the Navier-Stokes equations actually show that what are usually named mild solutions or weak solutions or Zine solutions might be very badly behaved. Okay, so that's an example. We saw examples related to stochastic PDEs and you name it. So there's various situations in which you can apply that. But that is one possible direction, and it looks more like a race to actually making counterexamples to what people might have believed. I mean, I've seen even like people commenting, why are you doing this? Why are you destroying our dreams? Well, it's a mathematical theorem. It's a mathematical fact. Actually, you're not destroying any hope or anything. It's, if you can prove that theorem, that is simply the reality of the consequence of the axioms you're working with. So if you can't do something, the problem is actually not in the method. The problem is in the concept of solution that you advanced. So you advance that concept of solution, I can prove to you that something actually happens. The only thing that you can actually question is whether the concept of solution is correct or not. And at that point, you have just simply two ways. Either you swallow that thing might happen. It's like swallowing that the continuous function might be not differentiable, which, for the mathematicians of the time of Weierstrass looked like a blow. So either you swallow that, or maybe you just say like, well, shit, I don't want to actually work then with continuous function. Let me just start with C1 right away, which is a legitimate reaction to the thing, right? But in a sense, the story does not stop over here, because you might ask the following question, which I've seen asked actually, for instance, by Sasha Schnirelman in some surveys. Would have Onsager liked our answer? I don't know, and I don't think anybody knows, right? I mean, unless you have a medium and you can kind of call his spirit and ask directly. And again, I'm not really understanding what is there to like or not. It's an answer, right? I mean, you asked whether something is true, and what I can do is just telling you, yes, it's true. Now, what you might not like is that you were maybe believing that, okay, this is true, but it's because these, Hoelder 1/3 solutions of the Euler equations were supposedly limit of Navier-Stokes. If you actually read Onsager's paper, he never states that. And I think he never states that because he's a clever guy, and in particular, he knows that Euler is reversible. So certainly you cannot pretend to understand limits of Navier-Stokes just by looking at Euler alone, right? In a very irregular regime. Of course, if you are in a regular regime, if the solution is very smooth, which essentially puts this infinite dimensional system very close to be finite dimensional, right? I mean, because when you go high in the Fourier modes, your perturbation, your correction is less and less important. In that case, of course, you might believe that you have a solution of Euler and you're able to perturb it to a solution of Navier-Stokes. That's very natural to believe. But if you have a very regular solution, not. And so another legitimate question is certainly, how far are we in terms of these solutions to be, limits of sequences of Navier-Stokes? In other words, to actually answer to the first question that I posed. In that sense, Onsager as a physicist might not have liked these solutions because certainly some of them are not solutions of Navier-Stokes. So let me pose this question, which is, I believe, the kind of beyond where you want to go. So, and the question is, which of these solutions are limits of Navier-Stokes of solutions of Navier-Stokes with viscosity going to 0. Okay, and interestingly, there's already an answer. So that was the first answer. In fact, all of them, if the solutions of Navier-Stokes are sufficiently weak. And so this is due to Buckmaster and Vicol. But somehow you're essentially dodging the question, because these solutions of Navier-Stokes are also extremely irregular, and they behave in a very regular way. In particular, for instance, they don't have finite dissipation rate at all. So the dissipation rate, in fact, is infinity for all of these solutions. So because certainly this was not what Onsager had in mind, let me then put an additional proviso over here. So which of these solutions are limits of sufficiently smooth solutions of Navier-Stokes? And what would you ideally understand as sufficiently smooth? Well, I'm not pretending we are in the three-space dimension, ideally, right? I'm not pretending that you first solve the millennium price problem and then you actually answer this question. That is maybe too much to ask. I mean, there's a very natural concept of solution which has been produced in the literature, which is that of Leray-Hopf-Wick solution. That would be a wonderful result. Or what are called admissible solutions in the sense of Scheffer and Caffarelli-Kohn-Nirenberg, which is kind of the best notion of solutions that we know, right? So maybe here I could ask Leray-Hopf or admissible. And it's interesting. So what is the notion of admissible solution and what is the notion of Leray-Hopf solution? Well, for Leray-Hopf-Wick solution, essentially you're asking that even though you don't have enough regularity for your solution to, oh, and very importantly, so these are solutions that you can actually prove to exist for all time, given any L2 initial data, okay? So Leray-Hopf, you will see that, you know, it's very natural for our considerations because what you're assuming is that U is a weak solution of Navier-Stokes, and the energy, what we derived as the energy identity is actually an energy inequality. Right? I mean, of course, the inequality that would go into the direction that you know, a physicist would like. So we don't have enough regularity to actually derive the identity over here, but what might happen is that there are singularities, and maybe these singularities help us to dissipate the energy even more. But certainly, it doesn't violate the energy inequality in the other sense. And what are admissible weak solutions? Well, admissible weak solutions are the ones which actually satisfy in the inequality form the pointwise equation that from which we derive this by integration. Okay, and the first very question that you actually can ask in here is that if you're hoping to pass into the limit into Leray-Hopf-Wick solution, then you'd better have that, you know, the energy is really decreasing in the limit so that this guy is less or equal than 0. And if you're like wanting to pass into the limit in admissible weak solution, so you better hope that when epsilon actually vanishes, here you get a 0, right? And so you get that this inequality is satisfied for your final solution. So the very first question that you can ask is, can I at least produce weak solutions of the Euler equation which pass these two tests? So do they have decreasing energy, total kinetic energy, and do they have sort of locally decreasing kinetic energy. So somehow, if you interpret somehow whatever is this one here as the local law, which is telling you whether energy is produced or dissipated at the local level, what you would like to have is something for which this one has no source. It only has kind of possible sinks. Okay? And it's not at all clear that having this inequality, which is an integrated version of this, really means that you're having that inequality. So one way is obvious, but the other one is very interesting. And so I already mentioned the work by Buckmaster, myself, La'szlo, and Vikol, which is essentially answering to this question. So yes, we can actually produce weak solutions of the Euler equations which at least pass this test. And then you probably heard Hyunju lecturing about her work with Vikram and Novak. It's not quite the Onsager conjecture in the sense of having 1/3 of derivative in the L infinity sense, but at least in some Bezov space, they are able to produce solutions which have 1/3 of the derivative, which is in L3, and which is satisfying the inequality with 0 over there. So solutions of Euler again. But of course, back to square one, these are still results on the Euler equations, and they're still not actually telling you whether you're able to approach your solutions of Euler via Navier-Stokes. Okay, so now.
When you talked about the Onsager conjecture, you mentioned the 3 different types. You had Onsager's definition of what counts to be a solution in terms of ODEs, a couple set of ODEs. You could say the same thing for the Navier-Stokes as well as a system of ODEs. Would that reduce to, would that be equivalent to one of these senses?
Okay, so if you actually write down Navier-Stokes in the sense of Fourier and writing down all of the Fourier series, you actually get the weakest notion of solution, the ones which are called Auxine solutions. Auxine solutions or mild solutions, at least if you so now here there's a provision, right? So the pressure only appears as a gradient. If you take the divergence of your equation, you actually have an equation for the Laplacian, which is Laplacian of P equal to something. So in the definition of mild solution, you actually postulate that the pressure is given to you by the singular integral operator applied to your nonlinearity. Now, it's only a technical difference. If you were on the periodic setting, you wouldn't see this, because once you actually solve the equation, the only difference between the pressure that I might have found and the pressure that you find by actually solving the PDEs is an harmonic function, which on the torus is a constant. On the full space, there actually might be an harmonic lingering over there. So, but if you take actually Onsager original definition and you apply it to Navier-Stokes, you actually get the Leray projection, which means you get these solutions which would have the pressure realized through solving the elliptic PDEs in the obvious way. But then it's actually the weakest notion of solution. So then you would actually fall into this Buckmaster Vikol, and for every convex integration solution, you would actually be able to find something which approximates in that sense. But they are very badly behaved. They are very rough to start with. Okay, so they don't even belong to the energy space. So really somehow, so here is, I think, something in which the application of the theory of convex integration really discovered something that was extremely surprising to people. I don't believe that before that work, the experts were seeing a big difference between mild solutions and Leray-Hopf weak solutions. Of course, they knew that proving for a mild solution something like Leray-Hopf was a tall order, because you would like to multiply your solution by U and make all of the computations that we have done, and they simply don't work. There's not enough regularity to do that. But I don't think they were expecting that there is such a monster actually lurking in background. But now what we learn from that work is that really this or that is a very severe constraint. Or just assuming enough regularity to be able to write down, for instance, this one, so that this guy is finite, is a very big constraint.
Initially, you derived the energy conservation by dotting the Euler equation
Yes.
with U and so on.
Yes.
Now, which part of that derivation changes for you to get this answer for these solutions?
So that derivation is now for these solutions at this level of regularity completely invalid. Because, you know, to start with, in your equation, you don't have enough regularity to actually declare that the derivative is a serious derivative, is a function. It's just a derivative in the sense of distribution. So now you're having a distribution which is maybe miserable. You know, it's a derivative of something. So if it were a Dirac mass, already would be a very strong information, right? It's maybe not even a measure. Maybe it's a dipole. And I'm now multiplying it by a function u, which is potentially very irregular. So I'm not even able to make sense of that multiplication anymore. So, and then even less so, I'm able actually to tell you that there is a product tool like Leibniz, and that I'm able to do like, you know, u dot grad u, or like, you know, it's gradient of modulus of u squared divided by 2. So if you want, the upshot is, one of the upshots of all of these constructions is that once you are at that low regularity level, not only you cannot justify your computation because, you know, at the mathematical level, I cannot make sense of the product between these functions, but it's more just than a technical problem. Actually, the equation does not hold. So it's, you know, it's in some sense, if you want to make sense of that equation, you start like facing problems like, you know, multiplying distributions. Can you do it? And if you can do it, in which sense you can do it? And of course, as we know very well, you can try to make sense of it, right? I mean, you can take, for instance, I don't know, a Dirac mass, and you can approximate it with something smooth. And you can take your other distribution, and you can approximate it by something smooth. Then you can actually carry on the product of the two smooth approximations. But then you face all sorts of problems. I mean, will this product actually converge to something meaningful? Will actually the convergence be unique? Can I pass into the limit, or does it depend on the way I regularize the problem? And then you see how, like, you know, this comes into play. Yes. The large? Oh, if you Fourier transform, yes, yes. Yes, it means essentially that the Fourier, you know, coefficients are going down like k to the minus 1/3, yes. Well, now it depends on whether you integrate over all of them or like taking. Yes. Yeah, okay, yes. Yes, okay, so this is what I'm actually going to explain at the level of energy conservation. So when I will actually prove you that the energy is conserved, I will try to argue in the following way. So that form of computation that you saw, that I want to, like, you know, that term, which I want to actually hopefully carry on some computation and say that it integrates to 0, it's actually the product of 3 functions. And these 3 functions all have like, you know, 1/3 of a derivative. So what I would like to dream is like distribute the derivative over there, which is a 1 full derivative, like, you know, unpack it into like thirds of the derivatives and distribute it among the 3 factors, and see that somehow I can of that quantity. Of course, this comes with a very big caveat, right? If I give you a Hoelder function 1/2 and I multiply it by another Hoelder function 1/2, I don't get a differentiable function. If I give you 2 differentiable functions and actually multiply them, I don't get a twice differentiable function, right? So there must be some very interesting algebraic identity which is going on, which actually allows me to distribute this derivative among the different Fourier modes. But yes, you are on to kind of the key idea or key insight, if you want, of Onsager. That at the level of Fourier, when you are actually above that regularity threshold, you're able to manipulate the Fourier coefficients in such a way that your quantity makes sense.
is there the issue that the integral over the moment I want the total derivative is not actually?
Yes, if you want, yes. Yes. When you are below the threshold, yes. If you want, yes. And that term is actually creating something, right? And somehow the upshot of the convex integration is that I can arrange a solution to sort of like, make that term, that source of energy, if you want, do pretty much what I want at the level of the total integral, for instance. Okay, so in principle, this was half of the talk, but I guess I stop here. Well, I mean, of course, I will have 4 lectures in which I will expand upon, like, various points of this one.
Before the question and answers, I want to present on behalf of ICTS a small memento. I think it's a sweatshirt and a mug.
Thank you very much.
So I have a question. Can you please give some sort of a situation where you can produce Euler as a limit of Navier-Stokes? Are there some situation in this where give positive answer to your first question?
Oh, my first one.
Yeah.
Like, can you produce the ones which are kind of dissipating with Navier-Stokes? No. That is what I would consider the holy grail, but not yet, at least.
But if you, for example, change the equation a little bit by adding force or something.
Ah, yes. Okay, so this I didn't say. So there's one thing that you can try to do. And you could just say, like, okay, let me put a force. Okay, now let me put a forcing term. And now, of course, the forcing term should be, though, not too bad, right? I mean, if I'm actually injecting a lot of energy at very high Fourier modes, then I will produce something. So what is a good notion of forcing term, or sort of non-trivial forcing? Well, for instance, one test that you could do is like, let me take a force which is the regularity, that regularity, and let me put it in the heat equation. If I will not see anomalous dissipation in the heat equation with that force, then if I see instead anomalous dissipation when I put that force into the Navier-Stokes equation, then that's a non-trivial example. Okay. So on the other hand, you see there's a borderline for the force that if I take the force which is too regular, and essentially too regular is if I take the force regular enough to apply well-Postner's theory of Euler, then it really becomes, again, a little bit like not having the force. It's so regular that I really need to do something different. So then the answer to your question is that I have a paper with Elia Brouet, and then a subsequent paper with Maria Colombo, Gianluca Crippa, Massimo Sorella, and Elia Brouet, all Italian people. And essentially what we can show is that if the force is below the level where you have well-Postness of a nice solution of Euler, so if the force is not Lipschitz, so C1 alpha would be well-Postness, then I can actually show you with the force examples of anomalous dissipation. They're not done through convex integration, though. They are done more through some mixing for the transport equation. So the way they are done is kind of, we produce 2-dimensional vector fields by solving Euler, and then we advect the third component with these guys, and that is where the source of dissipation is. So it's at the transport level, in a sense. So it's connected to the kind of anomalous dissipation for transport equations that La'szlo was talking about. But it's a different construction, and if you want, it's in a sense dodging. I mean, it definitely tells you that if you allow me to play with the force and the initial data at that point, okay, so I can produce something which is a non-trivial interaction at the level of the nonlinearity, which I don't see if I had actually the heat equation. On the other hand, having the force as a kind of like, jolly gives me so much freedom that the problem becomes considerably easier. So I cheated somewhat.
Are there any more questions?
Yes. For dissipation. No, I mean, not that I know of, like, a simple way of like seeing, oh, I look at that solution, it has like, this feature, then it necessarily has to dissipate. No. In particular, it could be a very irregular solution and still have energy conservation. Well, okay, so the scaling that I actually suggested, because there's lots of end waving arguments and like, what is typical and what would happen with probability 1 and so on, is maybe more like saying what you are expecting in a statistical sense is that I switch off epsilon to 0, and then with probability 1, I'm going to see something which is almost of the correct Hoelder regularity. It's unclear if it will be that or some logarithmic correction to that or not, and which is dissipative. But of course here, I'm just like, giving you some specific examples. So the statistical theory might actually tell you that something has to happen with, almost surely. And on the other hand, I might be able to cook up examples where that does not happen. But at that point, if you want to understand such a deeper question, I think you can't look at them sort of deterministically as we are doing. Okay, so definitely the examples that I've given you tells you, like there are solutions which are compactly supported in space and time, for instance. So they start with initial data equal to 0. So certainly there is no just uniqueness if you just have a solutions in the sense of distribution. Okay, then you might ask me, well, let us put, for instance, the constraint that the energy has to go down. If the energy has to go down and you start with 0, then there is no unique solution. Okay, but then La'szlo and I can actually construct multiple solutions even which satisfy that constraint. Okay, next you can tell me, put this guy, for instance, less or equal than 0. And then La'szlo and I can actually construct you things which satisfy that, and they're still not unique. There are several other things which have been proposed in the literature. So for instance, look at the maximally dissipative solution, the one that dissipates the most. Okay, even for those, you have actually counterexamples to uniqueness. So I don't know what are the possible, constraints that you might imagine on the Euler equations. So I would just say that so far, for pretty much everything that has been come up with in the literature to try to actually force some uniqueness criterion on the Euler equation seems to fail, and seems to fail with these convex integration constructions. But there's quite a few people actually believing that that's because we don't have the correct concept of solution. I personally would believe that it's really a fact of life. In particular, if you really make me drink enough, maybe what I would conjecture is that you take Navier-Stokes, which is going, with epsilon, which is going to 0. Sometimes it will not converge even to Euler, it will just weakly converge. Sometimes maybe it will converge to solutions of Euler, and I would imagine it might perfectly be that it depends on the sequence of epsilon that you're going to 0. And so at that point, you find simply different solutions of Euler, which are coming from different solutions of Navier-Stokes, for which I would be more inclined to believe that the solution to the Millennium Prize is kind of, on the positive side. So there are no singularities, or if there are singularities, maybe the solution is still unique. But, it's belief at this point. Sorry? Yes. So, for instance, assuming that it satisfies this inequality with the 0 over here, because epsilon is equal to 0, that is actually a definition which is proposed by Duchamp and Robert in kind of the 2000, something like that. Together with another equation, but what it means together with another equation? Well, but then the system, of course, becomes overdetermined if you don't put more unknowns, right? I mean, then of course you might try to do that, but then the local well-Posner's theorem, which tells you you have a smooth initial data, then you will have smooth solution, that will completely break down, because then you have an overdetermined problem. I mean, yeah, maybe, yeah, well.
How does the roughness change the time? Does it, are the solutions the roughness changes? Can start with that one
Okay, so when you actually are below the threshold, so when you are above the local, so the local well-Posner's theory for Euler, for instance, you would need at least one derivative. It would need to be C1 alpha. When you start with that, when you start with a C1 alpha solution, there is a C1 alpha solution for short time. And then actually there's the problem whether this norm blows up. And in fact, the C1 alpha norm, if alpha is sufficiently small, actually that blows up. It's a breakthrough result of El-Guindi by some years ago. But if you have higher derivatives, we don't know. Possibly. Now, if you actually drop the regularity, if you go just slightly below the Lipschitz regularity, then whole hell actually breaks loose. You can make examples which instantaneously lose regularity. So it's you are all of a sudden you're actually kind of traveling on the wrong side of a threshold, which makes the local well-Posner's theory in the classical sense somewhat non-meaningful. See, the local well-Posner's theory is more or less kind of reducing this infinite dimensional problem to a perturbation of the finite dimensional one, if you think about it, give or take. And when you are actually below a certain regularity threshold, you will not anymore be able to do that. So the nonlinearity will have such a strong and important interaction that you will not be able to sort of look at that as a perturbation of a finite dimensional system.
Just mathematical curiosity, can you produce better Hoelder solution using this method? Can you break the barrier?
No.
Or is there any physical reason that you
No. See, I mean, these solutions, when they are produced, they produce dissipation of the energy. And so the fact that you can prove that you have conservation of energy.
Just like hypothetical situation.
Hypothetical situation, whether you can produce kind of more regular solutions with convex integration. Now, after 10 years, I think I learned my lesson. So, because I was asked, can you use convex integration for Navier-Stokes? And before Buckmaster vehicle, I always said, no, it's impossible. I don't believe that. And then it was done. Can you produce solutions which have bound on the vorticity in 2D, LP bound? And that I said, no, categorically, no, that's impossible. And they just did it. So let me just tell you the honest answer, which is, I don't know. Certainly, I can't produce a solution with higher Hoelder regularity. Now, if you allow not to be Hoelder, so if you go on some Sobolev category with less summability, then it has even been done in the literature. I mean, it's a pretty hard. They are pretty hard results, but it has been done. But at the Hoelder level, I definitely don't see a way of producing solutions which are more regular than this using convex integration. But I am a very limited human being, as I've been proved, like, several times before. So I'm not going to say that it's impossible. It looks hard. No, I mean, physically goes beyond my, realm of expertise. I don't know what the nature is doing. I mean, my ambition are not that grandiose somehow. I don't really know. There's very important questions. For instance, if the answer to the Millennium problem is that solutions of Navier-Stokes actually develop singularities, right? I mean, is then any more a valid physical model for, reality? So, at that point, I don't know, honestly.
Okay, it seems there are no other questions. So let's thank Camillo again. Thank you very much for your time.